Hello, and welcome to Regents Science Live, the 2024 Chemistry Edition. My name is Mr. Bradley. I'm a chemistry teacher at New Hartford High School, and I'm really excited to be here with you guys tonight. I haven't done this in quite a while, so this is exciting for me. My first time back in front of the camera for over 10 years, but I have been in the classroom all those years, and I've got a whole lot of chemistry that I'd like to share with you guys tonight. So for the next hour, I'm at your disposal. We've got some wonderful chemistry students over here that are going to be helping out as well, answering your phone calls or answering your tweets. Please check your screen out right there for the phone number to call, and the tweet address is there as well. But we prefer that you call, because if you call, we get to hear your voice. We know where you're coming from. So don't be too shy. Make sure you pick up that phone and give us a call, okay? Folks, Chemistry Regents is, what is it? It's 8 p.m. right now. And the Chemistry Regents is at noon tomorrow. And so you've got less than 24 hours to pick up a few more of those really special golden nuggets of information to help you with that Chem Regents tomorrow. I know you've been working hard all year and doing well on this test. If you're watching this show right now, doing well on that test is important to you. So that's what I'd like to try to do this hour, guys, is to help you by answering your questions, by giving you some tips, maybe some little strategies to help you do well on tomorrow's test. And then, do your best and give it your best shot. So again, guys, the number's right there. Please call in with some questions. Now, while we're waiting for questions to start coming in those phone lines, I do have some things that I'd like to go over with you, some basics about the test. I've got some strategies to share with you in regard to how the test is structured, the kind of consistency that you see from year to year with the test that will help you be more prepared. The fewer surprises, the better, right? And so that's what we'd like to do. So I heard the phone ring. Was that a question? It was a question, all right. Yeah, Maggie, come on up and tell us the question. I'm gonna move over here. Maggie's gonna let us know what the first question is. This is Maggie. She's an excellent chemistry student, and she's here volunteering her time, so thank you, Maggie. Appreciate it. What question do we have?
We got a question about going over half-lives.
Half-life, absolutely. So just general go over half-lives. All right, I'm going to come over here to the white screen, or the Elmo. All right, let's talk a little bit about half-life. Okay, so, well, the first thing that we should do is recognize that there is a reference table right here. Now remember, guys, the Chemistry Regents, like your Earth Science Regents, is going to really rely on that reference table for a great many questions, right? And so this one right here, Table N, is titled Selected Radioisotopes, right? And what this is providing you with is a list of isotopes which are radioactive, right? What that means is that they will undergo decay. They will go through a decay process where they're going to emit alpha, beta, positron, gamma radiation, which is listed right here. And in doing so, they're going to become more stable, whatever they transmutate into, okay? So on this table right here, the second column is titled half-life. Now, if you look at half-life, we want to recognize what it is, right? Half-life is time, okay? It's always time. And if you look down the column here, you'll see you could have a half-life that is days, right? So gold 198's half-life is 2.695 days, all right? You could have half-life that is in years, like carbon-14, which is an important isotope we should talk about. We'll mention it before we're done. That half-life is over 5,000 years. And look at this one right here. Calcium-37's half-life. What does MS stand for? Well, that M is milli, and the S is seconds. So that means that half-life is far less than 1 second, right? It's 182 milliseconds. So half-life is time. Now, what is it the time of, right? Well, let's do carbon-14 actually, because that's an important isotope that you want to know what it's useful for, okay? So let's talk about carbon-14, right? Let's say that you unearth a bone from an archaeological site, and maybe you're thinking, wow, I wonder if could this be a woolly mammoth bone? Woolly mammoth were ice age creatures going back tens of thousands of years, right? And one of the ways that you could try to determine if it could be a woolly mammoth bone or if it could be a Neanderthal bone or whatever it might be is by looking at the amount of carbon-14 that remains in the bone. Because all living creatures have a basically static amount of carbon-14 in their body as a ratio, right? And that's because every day you eat food, you consume carbon, and as the old carbon-14 decays, it's replenished with what you are providing with yourself through again, eating. But then eventually that creature, the woolly mammoth, whatever it is, that creature passes away, no longer is eating food, at which point the amount of carbon-14 starts to decline. It starts to go down, right? So let's throw some numbers out there that are just easy numbers to work with, right? Let's say that you had 200 grams of carbon-14 in the bone at the time of death, right? When the woolly mammoth was eaten by a saber-toothed tiger, right? So I'm making all this up. Please don't think that any of that's accurate. So you have 200 grams. Now, there's 3 ways that we can try to measure half-life changes, right? We can do it in grams. We can also do it in percentage. Now, so for example, the amount of carbon-14 at the point of death for the animal would be 100%. It's the starting amount, right? So we can do mass, we can do percentage, but then the one that the Regents really does seem to prefer is fractions, right? Now they're all fair game, but I think if you look at the most recent exams, it's pretty much fraction is what they like to ask about. So what is the starting fraction when you're talking about the half-life? Well, you can write it a couple of different ways, but what I like to do with my students is I say, if you have the whole pie, right? Remember when you learned fractions, it was like you take a pie, you cut a pie in half, right? If you have the whole pie, then the fraction would be 1/1. It's the whole thing, right? You could say just 1, but it's a fraction, so might as well just keep it consistent. Okay, now, what are we trying to do here, right? Well, let's say that we look at the woolly mammoth bone and we're trying to understand how old it is. Well, that time right there for carbon-14, 5,715 years is its half-life. And it's called half-life because that is the precise amount of time that is required for all of these quantities to be cut exactly in half, right? So in other words, I like to draw this like it's a little chronology, like a timeline. I'm going to say that after the first half-life, right, which is 5,715 years. Now, I'm not going to keep drawing this bone over and over because that's the best artistic talent I've got, and I can't repeat it. So I'm just going to say, after one half-life, the 200 grams is now 100. Now, you may ask, well, what happened to the other 100 grams? Did it just disappear? Well, not truly. It didn't actually disappear. What it did is it went through beta decay, and it turned into a different element. It turned into nitrogen, actually. So it's not as though the atoms ceased to exist, but they turn into a different element. That's that whole transmutation part of nuclear reactions, right? So 100 grams remains. What about the percentage? Well, that would be 50%. And then again, I said that the fraction is the one that the Regents really seems to focus on most. So if I started with the entire pie, the 1/1, right, what would remain after the single half-life? Well, you would now have 1/2, okay? So that little picture right there represents the passing of one half-life. Now, what if time continues to pass, right? Because remember we said if it's a woolly mammoth, we're talking tens of thousands of years, right? Well, you examine the bone and you're looking to see how much of it remains. So let's continue this little half-life timeline here. Let's say, okay, I'm going to have my second half-life. Now, what I like to ask in my class, I say, well, how many years will that second half-life be? Because you might be tempted to think, oh, it's the second half-life, so that means more. No. Half-life is unchangeable, and that's another thing that you want to know for this test is it's really great that we can use half-life to help us learn and understand the past, But it's also unfortunate that, well, depends on how you look at it, but we can't manipulate half-life. In other words, if you have radioactive waste from a nuclear power plant, or if you had radioactive emissions, say from some accident with nuclear power or whatever you could imagine, you can't make that radioactive material safer by accelerating its half-life. You can't change, right? So in other words, that was 5,715 years. The second half-life must be the same amount of time. Half-life is unchanging, right? Now, what does change is the amount of that isotope. We're now past 2 half-lives. So originally we had 200 grams, but it was turned into 100 after 5,715 years. What remains now after another 5,715? Now we have only 50 grams, right? So I'm cutting, again, in half the prior sample. What happened to the 50%? Well, now it's 25%. And then the fraction, this is where you gotta be careful, right? How do I take 1/2 and cut that in half? By doubling the bottom number, the denominator, right? So the 2, 1/2 becomes 1/4, all right? So now, let's say that I examine that bone and I realize that compared to a living creature, there's only 1/4 the amount of carbon-14. That means that that bone is approximately 11,500 years old, right? Is that old enough to be a woolly mammoth? I don't know. That's where my knowledge of woolly mammoth ends. But let's go one further, because usually we like to go a little further with this half-life. So let me go right here and say, okay, we are going to go even further back in time. We're going to say the third half-life, 5,715 years. How much of that carbon-14 now remains? You would have only 25 grams remaining. You would have only 12.5%. And the fraction, now I tell my students here, be careful, because you know the little mental error you can make? You can say 2, 4, and then sometimes people write 6. But remember, half-life means that you're cutting the sample in half. So what's half of 1/4? 1/8. My helpers over here, they want to shout answers out. I can hear them telling each other answers because they all know this stuff. They're ready to go tomorrow. Taylor, you already took it. Okay, do we have another question coming? I think we might. Taylor, is there one in queue? Wonderful. So I hope that helps with half-life. If there's any more half-life questions, more specific, you want more detail, please call in. All right, got another question?
Yes. We have a question about going over changes in reactions and how to identify them.
Changes in reactions and how to identify.
Like different types of reactions and how to identify them.
Okay, we could do that. All right. So the question was changes in reactions, how to identify them. I'm going to steal a little piece of paper over here. I brought a little survival guide. And the reason I'm going to do that is because that question is a great question. It's a big question, meaning that there's a whole lot there. So if you have anything more specific, please call in. If I don't answer anything that you were looking for, please call in. But let me go over some of the basics of reactions. And do I want to use this to help? Yeah, I think this, rather than me writing them up here, I could probably give you. All right, so when it comes to reactions in your chem class, you learned early in the year, you learned what are called inorganic reactions. And these are the reactions that are called synthesis, decomposition, single replacement, double replacement, those 4 reaction types. Now, sometimes teachers will include a 5th one called combustion. Even though it's not inorganic, it is so central to so much that we do in chemistry. Sometimes we sneak it in early just because we want you to get exposed to what combustion is, right? And then quite a bit later in your chemistry year, when you did organic chemistry, you learned a whole nother set of reactions which are called organic reactions. I'm not going to go there. I'm going to stick with the inorganic and the combustion simply because there's a lot there, okay? So what are the 4 inorganic reactions that you will definitely need to know for this test? They're on there every single year, right? Well, the first one we said, let's see if I can get that, there we go. The first one we said, guys, is called synthesis, right? Synthesis reaction. And a synthesis reaction, that word synthesis, I believe you guys learned that word in Living Environment. It literally means to make, right? So when you hear synthesis, you want to think to yourself, the pattern of synthesis is always the same. You're going to have two or more, could be more, but you're going to have at least two of the reactants, right? These are your reactants right here. And what happens in synthesis is those two substances, whatever they are going to chemically react, and in doing so, they're going to combine into one thing. Two reactants combine to make one, and there's your product right there. So in this case, I've got sodium and chlorine, and they're both bonding to make sodium chloride, table salt, right? Right here, I've got iron and oxygen, and they're bonding, and they're making iron 3 oxide, right? So that's your synthesis reaction. It's a simple, straightforward reaction, right? Two things alone have to come together and make one thing separately or solely, right? Okay, what's next? We've got decomposition. And I believe that's another word that you came across when you were doing living environment as well. Decomposition means to break down, right? So one thing that I always tell my students is it's very rare that we use words in science that don't have some underlying meaning, right? So all of these terms that you use in science, there should be some meaning attached to them, right? Synthesis means to make. Decomposition means to break down, right? And so that's exactly the pattern that you're looking at here. If you look at decomposition, I will always have just one reactant, only one thing, okay? And that one thing is going to have to break down into multiple things. Right over here on this side, there's my product where I have two things separated away from each other, okay? So essentially, synthesis and decomposition are just the reversal of each other, right? So if you synthesize something, if you reverse that, you're decomposing it, okay? Now, there are ones that are a little trickier though. We've also got something called single replacement, okay? And again, words have meaning in science, right? We don't pick these names arbitrarily. So think about what it's saying. It says single replacement. What does it mean? You know, if you're playing a sport and you have replacements, you have substitutes, right? It means something's coming out and something else is going in, right? You pull your center fielder and send in someone new, right? It's the same thing with single replacement. You will always have an unbonded element, and it's going to try to replace an element that is bonded. So in class, we say a guy shows up to the dance and he's trying to steal the date, right? Trying to show up and say, I can steal the bond, right? And the only way that works, right? So let's look here. Can zinc steal the bond from hydrogen? Now, why am I saying hydrogen? Because the way single replacement works is that you're going to either switch your positive ion for your positive ion, or you'd switch negative for negative, right? And so because zinc is a metal, and zinc will form a positive ion right there, that means it's going to want to switch with another positive ion, right? And now, how do I know who the positive ion is? The positive ion is the one that's written first in the formula, and the negative ion is the one that's written second. So that means hydrogen is the positive ion here, and zinc is going to try to steal that hydrogen's bond, right? It's going to try to kick the hydrogen off and bond with chlorine. Now, the question is, can it do it? You have to know how to predict if it will happen. Here's how you do it. There's one table, table J. I always get lost in my reference tables once I fold them. Okay. Table J is the table that lists the reactivity. It's called activity series, right? And essentially what this is doing is it's ranking your elements in order of how chemically active they are, which is another way of saying how likely are they to react, right? So here's the rule. If this zinc is going to steal hydrogen's bond, right? If zinc is going to dance with chlorine, zinc has to be more active than hydrogen. Is it? Here's zinc. Who's he trying to steal from? Hydrogen. Can zinc replace hydrogen? Absolutely. Which means if I put these two chemicals together, there will be a spontaneous reaction where zinc bonds to chlorine and hydrogen gas is produced. So you see bubbling, you see heat, or you feel heat, right? And that's actually a reaction that I'm almost certain you would have experienced in your chem lab at some point. There's so many different things that your teacher probably could demonstrate to you through the zinc and hydrochloric acid reaction, right? Single replacement being one of them, okay? All right, now, real quick though, what's the second reaction here? Well, the second one, it says no reaction. Why does it say that? Copper trying to steal the bond from hydrogen. Can copper do that? We already located hydrogen right here. Where's copper? Copper's below it. That means that copper is less reactive. Copper cannot show up to the dance and steal that dance, right? So copper, no, you cannot take hydrogen's bond. And so if I put copper and hydrochloric acid together, there will be no spontaneous reaction. There's no reaction there, okay? All right, so that's single replacement. What else do we have here? Double replacement. All right, again, these reactions, they get a little bit involved, right? Now, try to think about what the name is implying. Words have meaning. Single replacement. I know replacement means switching, right? I know single means that there is a single unbonded element, like the zinc we just looked at. So what does it mean to be double replacement? Double replacement means that instead of having one switch out, you have two switching. So here is your positive zinc ion bonded to chlorine. Here is your positive silver ion bonded to nitrate. What will happen if you put those two together? You will get a reaction where zinc takes the place of silver and silver takes the place of zinc. That means that you now have zinc nitrate and you have silver chloride. Now, how do you know if that's going to happen or not? How do you know if it's spontaneous? Well, it's not as easy as the single replacement, and it's not 100% predictable in the same way. However, there is one thing that you can do that you will almost certainly have to do on this test, right? I always tell my students as we're going over old tests, there are some pretty solid guarantees, right? And one of them is that you will have a table F question, right? Now, what is table F? Table F is the table that tells you whether a substance is soluble or insoluble, right? Now, soluble means it dissolves. Insoluble means it will not dissolve. And it's based on the ions that compose it, right? So, why am I talking about this? Because with double replacement, very often you will have what's called a solid precipitate, meaning that when you put the two chemical solutions together, bam, you see a solid form practically instantly. As far as our eyes can tell, it is instantaneous. And this is another thing I'm sure that you would have seen throughout the year. Sometimes it's a white solid, like you put together two clear solutions and all of a sudden a white powder or a white cloudy thing appears. There's another real cool one where you do lead and potassium, I believe, lead iodide, potassium nitrate. And when you mix those, you get a bright, bright yellow solid that forms almost instantly. So, if one of my products is a solid, that is a very strong indicator that this is going to be a spontaneous double replacement reaction. Now, let's look. Zinc nitrate. Now, how does this work? It's basically you're hunting for ions. Can I find, oh, look at that. I just found it. That's my nitrate ion. Now, look at what column it's in. Soluble. That means nitrate will form substances that dissolve. Now, I got to be careful, though, because this table also has a column that's called exceptions. Does nitrate have any exceptions? None. So I know that if nitrate, the NO3, if it's in a compound, it is soluble. Oops, I'm pointing at the wrong one. There you go. There's nitrate right there. It is soluble. It will dissolve, okay? So that one's not a soluble. Oh, check that one out right there. Silver and chlorine. All right, let's go on the hunt for ions again. Silver, chlorine, where are you? Ah, there we go. There's chlorine. It's also listed as soluble, so you might say, well, I guess I didn't find it, but wait a minute. This one actually does have exceptions listed. Silver, lead, mercury. Now, what does that mean? It means that if it's bonded to an exception, it will be insoluble. Basically, it's like it's reversing what that title says. So, hey, check it out. It's bonded to chlorine. Or excuse me, it's bonded to silver. Chlorine, silver, exception, which is why if you look there, you can see it's labeled with the little S. It is a solid precipitate, okay? Wearing black in a studio with a lot of lights, so I'm gonna wait my face. I told you girls I was gonna be sweating. It's actually not as bad as it was this afternoon. Whew. Okay. Now, I told you guys that we would do combustion, so I better do combustion as well. So those are your 4 inorganics. You're definitely going to see that somewhere on the test where you got to identify those. I'm going to flip all the way to my organic unit, and I'm not going to go through all of these because I want to try to get as many questions as we can, as many questions in as we can. However, here's combustion. Yes, combustion. My students, I think, sometimes get tired of me saying, you can't imagine how important this is, because I say it about so many things, right? But in terms of just the evolution of humans, I mean, the fact that we learned how to manipulate fire, that fire allowed us to stay warm, it allowed us to fend off animals, it allows us to cook food, and then that fire becomes the Industrial Revolution. I mean, it's, the idea of combustion is intimately tied to the human species, right? So that's a pretty darn important reaction, right? So what is combustion? Combustion is when you take a fossil fuel, right? And that means it could be methane or butane or propane or any fossil fuel, or coal, you could say oil, petroleum. Now, what does it mean to be a fossil fuel for this class right here? Well, we generally identify them as being hydrocarbons. You remember learning about hydrocarbons in your organic unit, right? That right there is C3H8, that's propane. It's carbon hydrogen, right? And then if it's gonna combust, that means you're gonna burn it. Gotta have oxygen. So anytime I have a hydrocarbon plus oxygen, that's my burning, that's my combustion. And I will always make the same products when it's burnt efficiently, and that's gonna be carbon dioxide and water. So that, in terms of your pattern, you're looking for a reaction type, that's a very easy pattern to identify. Hydrocarbon, oxygen, you always make carbon dioxide and water. Which, if you remember your living environment, you can try to relate that to the reverse of photosynthesis, like that whole photosynthesis and respiration. It's kind of the same thing, except this is from something that died millions of years ago, right? So, okay, so that was a lot of info on reactions. I hope that was helpful. And let's see, do we have any other questions? All right, Maggie. What do we got?
Our next question was to go over electrolytic cells.
Electrolytic cells, all right. Thank you, thank you. Well, let's see, guys. To go over electrolytic cells, I at least got to mention both types of cells. So I'm gonna keep referring to this just because it's easier than me trying to draw some diagrams that could get a little messy, okay? So let's talk about electrolytic cells, but I want to make sure that I do a little comparison to the voltaic cell, because you got to know both of them, right? So, words, got to know what words mean, right? Words are important. If you notice the title at the top of this page, guys, it is electrochemical cells. And we don't want to get confused, because we could say electrochemical, electrolytic, they're not the same thing. Electrochemical is the big umbrella, right? The big overarching title. It means chemical and electrical reactions, right? Under that umbrella, there are the voltaic cells and the electrolytic cells, which the caller asked for the electrolytic, right? So let's just do a real brief on the voltaic, and then we'll look at electrolytic, right? What do you want to know? Well, you want to know that a voltaic cell is spontaneous. Voltaic cells are basically batteries, right? They are going back to the original design of batteries, where they were stacking metal discs and stuff like that. It's a spontaneous reaction where you take chemical energy and it will convert to electrical energy all on its own. All you gotta do is let it happen. Just like when you plug a battery into your cell phone, your laptop, your remote, whatever it is, it just does it on its own because it's a spontaneous chemical reaction, right? Well, then you got electrolytic. Now this one looks different here, right? This one is not spontaneous, and that's a key idea here. Why is that so important? Because one of the distinctions that you'll see with voltaic versus electrolytic, the electrolytic must have its own power source, right? So if you look at these two diagrams, this one is a battery, this one requires an external battery, or sometimes they just say power source. Excuse me. So, let's see. There's my power source right there. There's my power source right there. Now I'm going to, well, let me say one more thing and then I'm going to put this aside so I can draw it a little bit bigger. We said the voltaic was spontaneous, chemical to electrical. The electrolytic is not spontaneous, electrical converted into chemical. So it's the reverse process, right? One way you can think about it, by the way, guys, so a great example is that when you use your device, you are letting the chemical reaction convert to electrical energy to use your phone, right? But at some point that battery is dead. The chemical reaction has stopped. And then you plug it in. And when you plug it in, what are you doing? You're reversing non-spontaneously the electrical energy from the outlet to store chemical energy back into your battery, okay? All right, so let's take a look at an electrolytic cell. One of the most common examples that they'll use for electrolytic cells is what's called electrolysis. And that's a word that you guys would have learned. And electrolysis is the process where you take a chemical substance, and one of the common examples, which is something you can do pretty easily even at home, but certainly in a chem lab, if you take liquid water and you pass an electric current through it, you can cause it to decompose. And when you do that, you're going to get hydrogen gas as well as oxygen gas, right? And if we balance this, we want to put a 2 here and a 2 here and a 1 here, okay? And so this electrolysis is an example of an electrolytic cell. Now, what does this look like as a diagram? Well, I have to have a power source. Sometimes it's just labeled battery, sometimes it's power. It's going to have those little hookups. Maybe you could draw it so it looks kind of like a 9 volt. One of them will be the negative terminal, one of them will be the positive terminal. And you're going to hook that up to your solution where you have your H2O, and you have to have some electrolyte in there in order for it to conduct the current, okay? But you'll have your H2O in here. And the way they draw this usually is to have a couple of upside down test tubes. And you're going to have a hookup, a little electrode to one test tube, and then you'll have a little hookup, oops, to the other test tube, and then right here is where your H2O is going to be broken apart by that electric current. Excuse me. So, how do you figure out where it's going? Well, when you look at this cell and you're trying to determine what is happening, the first thing that you have to do is identify the direction of electron flow. It's the same thing as the voltaic. You got to know which way the electrons are going. But the way that I do it is by looking at these symbols on the power source. Now, I know that electrons will flow through the wire, right? Electrons move through the wire. That's your electric current. How do I know which direction they're going? Well, I know that electrons have a negative charge. And one of the fundamentals of science that I learned a long time ago is that opposites attract, but like charges repel one another, right? So, this is a negative terminal. This is a negative electron. Does that electron want to go there? Absolutely not. The electrons are going to be pushed out of that terminal. And if I follow them, that means that they're going to go all the way here to this electrode right there, okay? Now, what about these electrons? Well, they're negative. Are they going to want to go to this positive terminal right here? Absolutely. Opposites attract. So that means that these are going to want to go there. So that means that this right here, this electrode is losing electrons. So what does that allow me to do? I know that this test tube right here is loss of electrons. I know that this test tube is gain of electrons. And once I figure out the loss and the gain, then I can figure out who's been oxidized, who's been reduced, who is the anode, who is the cathode, and I can basically figure out the whole cell, right? So let me use oh, you know what? Actually, I want to put this here. It's one of those things that I brought. I said I was going to try to give some strategies, some tips, right? I know that your teachers all share with you different little mnemonic devices and acronyms to help you. And there's so many of them out there. This list right here, there's only 7 of them on there. But these are the ones that I really feel confident are guaranteed on the test. You're going to use these little memory devices, right, on the test. So at the very bottom, I bet those look familiar to you guys at home, right? Leo the lion goes, Maggie, do you remember that one? What does Leo the lion do? She said grr really loud over there. Leo the lion goes grr, right? Now, why is that important for me? Because Leo tells me that loss of electrons is oxidation. And how do I know that I've lost electrons? Because my charge goes up. Now, who lost electrons here? This right here did, right? This is the one that was having the electrons yanked out by that power source. So that means that this right here, this test tube, is where oxidation is occurring. That is my oxidation test tube, right? Leo the lion goes grr. Gain of electrons is reduction. How do I know if I've been reduced? Because my charge goes down. Now, this one right here is gaining electrons. That means that this test tube is where reduction is happening. Okay, now I can go even further. If I know who's oxidized and who's reduced, then I can also label who is the cathode and who is the anode. And that's where this other saying, red cat and ox, that's where this one comes in. So I know reduction is the cathode, red cat. Gain of electrons is reduction. Ah, right here, this is my cathode. By the way, when we do this in class on the board, I tell my students ahead of time, the board is going to be absolutely filled. So try to write neatly because there's so many things, so many moving parts in these electrochemical cells, okay? Okay, well, we got red cat and we also have anox. Anode is the oxidation. And so here's my oxidation, that's my anode, which is the positive electrode on that cell. All right, boy, I'm not done yet though. Electrochemical cells have got a lot going on. Let me look way back up here at this reaction right here, okay? Now, that reaction, by the way, one thing I want to make sure I point out, guys, whenever you get the voltaic or the electrolytic cell, the diagram can be potentially confusing with a lot of moving parts, right? But they will also always give you an equation to look at. That right there is your equation. And everything that I just did, I could probably find almost all those same answers with just the equation. Not all of it, but a lot of it, right? So let's look at the equation now. If it's a redox reaction, and I want to figure out who's been oxidized and who's been reduced, right? The first thing I have to do is put my oxidation states across the top of my equation to figure out whose numbers have gone up, whose have gone down, right? So I look at the equation. Rule number 1, don't forget it. If an element is by itself, it's elemental, it's not part of a compound, that means that its oxidation state is 0. It's got no charge, it's neutral, right? So this hydrogen right here is elemental. That means it has a 0 charge. This oxygen, 0 charge, okay? Now over here is where I have my compound, and that means that they're not 0. That means that they are ions, potentially ions, but either way, they do have an oxidation state, right? So the oxygen, oh, where'd my periodic table go? The oxygen is going to be that 2 negative that I see right there on my periodic table. And when you look at the hydrogen, you got a couple of choices there, but remember the rule is that you have to have the total charge of the compound equals 0. So that means the hydrogen is going to have to be positive. It's going to be a positive 1. And so the H2 means 2 of those positive 1s to cancel out the negative 2. All right, okay, so now I know. Now let's go back and see. Loss of electrons is oxidation, and my charge goes up. Whose charge went up? Hydrogen, you were a positive to begin with. You turned into a 0. Hydrogen, you did not go up. You were not Leo'd, were you? Okay. Oxygen, you started as a 2 negative. Oh, you went up, right? Now you might say to yourself, wait a minute, how's that going up? Well, on a number line, 2 negative to 0 is up, right? So that means that the loss of electrons occurred to the oxygen ion, the 2 negative oxygen. Now, why do I want to know that? Because now these test tubes can be finally filled. Oxidation, loss of electrons. That means that this test tube right here, remember we said it's going to fill with bubbles of gas? This is where the oxygen is accumulating because that's where the oxidation is taking place. Now, gain of electrons is reduction. Excuse me, charge has to go down. Hydrogen, you started as a positive 1. What did you turn into? Ooh, you went down to 0. Grr, you went down. Okay, that means that it was the H positive that was reduced. And that means that the H, there's the little bubbles of gas, and there's your H2 right there. It's getting messy, like I said. It's hard to keep track of all those things on those cells. But that is pretty much everything you can do with an electrochemical cell, or electrolytic cell. There's one other thing let me throw in there right now. Girls, is anybody waiting on a question for half reactions right now? Okay, perfect, because that's what I was going to do. So why don't we have that question, and I'll mop my head while you guys are reading the question, okay? Who's up in the queue? Taylor, all right.
Someone had a question on redox half reactions.
Excellent. Thank you very much, Taylor. Okay, so I'm glad that question was hanging out there, guys, because I was tempted to stop this right here. But now the question is, what about redox half reactions, which is going to apply to this? So you know what I'm going to do? I'm going to put this aside, but stay tuned. Don't go away because I'm going to come back to that, okay? But first I want to just do like a general look at half reactions. Okay, so by the way, half reactions are on this test. You can guarantee you're gonna have to write one for sure. You may even have to identify one inside of a multiple choice question. Okay, so let's look at 2 examples. All right, let's look at a synthesis reaction. Let's say that you had, I think this is the one that we just looked at in the book. Let's say you had some sodium metal, and you're going to react it with some chlorine gas, and from that you're going to get plain old table salt, right? NaCl. I'll put a 2 there and a 2 there to balance it, okay? Now I'm going to do another one here. Let's do a single replacement because that's also redox. Let's say that you've got some magnesium metal and it's all alone, single replacement, and it's going to show up and it's going to try to steal the bond from, well, let's do this. Lead 4 fluoride. All right. Does it matter that it's lead 4 fluoride? Probably not. Okay, so that means that the lead is going to be all alone. Why is the lead all alone? Because the magnesium bonded to the fluorine, which means I got to do that. There we go. Okay, now we're talking about redox half reactions, right? So these are both redox reactions. How do I know that they're redox reactions? One of the little tricks that you can use on this test that will help you recognize a redox reaction. If you're looking at an equation, at a reaction, and it's redox, the first thing you're going to do is put the zeros on the elements that are unbonded. And if they don't have those unbonded elements, then you're almost certainly not looking at a redox reaction on this test, okay? So look at this first reaction right here. Do I have anybody that is unbonded and gets a 0? Yes. Sodium, you're all alone. That means that you are a 0 neutral atom. Chlorine, I know it says Cl2, but it's still elemental. It's still neutral atoms all on their own. Okay, now I'm going to do the same thing down here. Magnesium, you get a 0 there. Lead, you get a 0 there. Okay, now the first thing I do is I put my zeros in. And if you don't do that, you will never come to the right outcome, right? Now I'm looking at the compounds, and I got to find what are the oxidation states of the ions in the compound. Now, sometimes this is easy, and sometimes it requires a little bit of problem solving, right? This one's easy. Now, why is it easy? Because look at sodium on your periodic table, right? Sodium has only one oxidation state. It's a 1+. You don't have to figure out anything. That's your answer, right? Chlorine, well, chlorine looks like it's got a whole lot of choices there, but if you remember that the positives and the negatives, they must cancel out to get to 0, well, then chlorine is going to have to be a 1 negative. There's no choice, right? Okay, so this is a 1+. This is a 1 negative. All right, now I got all of my top numbers there, which means those oxidation states will tell me who's oxidized and who's reduced. Let's do the same thing here. Now this one right here, PbF4. Well, you got a problem. Or, as a friend of mine is fond of saying, you have an opportunity, right? Lead has 2 choices, 2+ and 4+. How do I know which one to use? Well, you don't until you solve it. It's bonded to fluorine. Fluorine's a 1 negative, no choice, right? So I'm going to put the 1 negative there. Now, because I remember that you have to cancel out to make 0, that means that this lead will have to be a 4+. Why does it have to be a 4+? Because the formula is PbF4. So that means if I have 4 of the fluorines, that's 4 total negatives. I got to get the 4+ there, right, to cancel it out. And the other thing you can do, if your teacher taught you to do the crisscross, is a little way you can kind of cheat to get your answer. I shouldn't say cheat. It's a shortcut to your answer. It's not foolproof, so make sure you check your math. But okay, all right. So then let's see this last one right here. Oh, look at that, magnesium. That one doesn't need any work. It's a 2+, and we already looked at fluorine. Okay, 2+, 1 negative. All right. Now you had to do all that work, and we still haven't even written a half reaction, right? Well, it's okay. On the Regents, they almost certainly will do some of that work for you. Generally, they give you the numbers, and then they'll ask you to do a half reaction. They don't always do them all together, but you could have a different question that asks you to do the numbers as well. So it's good to make sure we know how to figure out those oxidation states, all right? Now let's do the half reactions. Oxidation, reduction. Okay? Now, I gotta go back to it here. When you're trying to understand redox reactions, redox is one of the tougher units that we do in chem, right? You need all the help you can get to keep this stuff straight in your head. That's why I'm always saying in class, Leo the Lion. Taylor, what does Leo the Lion say? Grr. There you go. Very good. Get some good gurs here. Leo the Lion goes grr, right? And that's going to be so helpful to you because it will help keep your confusion from going out of hand because you know those facts are true. Now, what does that mean again? I'm going to repeat it because it's so important. Loss of electrons is oxidation. My charge goes up. Gain of electrons is reduction. My charge goes down. All right, okay. Sodium. Did you go up or down? You started at a 0. You turned into a +1. Sodium. Leo got you, right? Loss of electrons is oxidation. So that means that the oxidation was the sodium 0. Now, finally, let's do a half reaction. What is a half reaction? Well, it means that I'm going to take the equation and I'm going to only represent what is happening to the single element that was either oxidized or reduced, right? In this case, it was oxidized. Now, the way I like to do this, guys, it helps if you kind of tell a story. You ask the element, what did it do, right? So in other words, sodium. What did you begin as? Well, sodium, you began as a 0, right? Sodium. What did you turn into? Sodium, you turned into a 1+. So I'm going to say sodium, you turned into a 1+. Now, sodium, how did you go from a 0 to a 1+? Well, we already know. You lost electrons. All right, now here's the key. To do your half reaction, you got to show what did it begin as, what did it turn into, and where did the electrons go, right? In this case, the electrons were lost, and so the electrons, because they're being lost, must be represented as a product. You gotta write them on the right-hand side of the equation, okay? So that would be the oxidation half reaction. Now, what about the reduction half reaction? It's really similar, okay? You're still telling a story about charge and electrons, right? But there's one very key difference here, okay? Now, gain of electrons is reduction. Your charge goes down. Chlorine, what happened to you? Chlorine, you started as a 0. Chlorine, what did you turn into? Chlorine, you turned into a -1. That means your charge went down. Grr, got you, right? How did you turn into a -1? Because you gained electrons. Now, in a chemical equation, if you're gaining electrons, they must be written as a reactant. And so I have to show the electron on the other side, which the reactant, the left-hand side of the equation, to represent that those are electrons gained, okay? That's my oxidation half reaction. That's my reduction half reaction right there. Now, let's do another one. I'll go a little quicker this time here. We already have all of our numbers. So we're just repeating the process with different elements and different numbers, but it's the same basic formula, right? Oxidation, reduction. Whose number went up? Let's see. Magnesium, you started as a 0. Magnesium, you turned into a 2+. Okay, so Mg started 0. Mg turned into a 2+. Magnesium, how did you do that? I lost 2 electrons, right? They're products because they were lost, okay? Reduction, let's see. Lead, you started as a +4. What happened to you? You turned into a 0. That's down, that's reduction. Now, by the way, stop for a second here. What about fluorine? Fluorine, you didn't do anything. You were -1 and you're -1 again. So fluorine, your oxidation state didn't change, and we got a name for those, although I don't think you'll see it on your test tomorrow, but they're called spectator ions. They're ions that are watching the action, but they're not actually exchanging any electrons, okay? So, all right, lead. You started as a 4+. What happened to you, lead? You turned into a 0. How'd you do that? You gained electrons. So they have to be written here, +4e. Excuse me. And those are your half reactions, okay? So they don't look exactly the same, but they use the same rules, the same patterns. Now, remember this thing right here? You can do half reactions for all of those electrochemical cells. And in fact, guys, on the test tomorrow, I would say that if you see an electrochemical cell diagram, if they show you the voltaic cell, this is on short answer, by the way, if they show you the voltaic or the electrolytic, it's a pretty good chance that you will have to write a half reaction that corresponds to the cell. And I'll just remind you what I said earlier, guys, is when you see the diagram, and these diagrams can look a little daunting, remember, they must give you an equation, a reaction that corresponds to it. And sometimes it's easier just to look at that equation and use that as your guide. So here's my equation. Look at that. We already did the work. Oxidation. Whose charge went up? Hydrogen, you were positive, you went 0. No. Oxygen, you were negative, you went 0. That is going up, okay? So that means oxygen, you started as a 2 negative, you turned into a 0, and that's because you lost 2 electrons. Remember, electrons are negative particles, so losing electrons actually raises your oxidation charge, right? Your oxidation state. Okay? Reduction. Hydrogen, you were a positive, you gained an electron. And when you did that, you see that positive? Canceled out. Hydrogen, now you're a 0. Okay? So there's 3 different examples of those half reactions, 3 different reactions to go off of. All right? So yeah, half reactions, definitely on the test tomorrow. Definitely an important part of that redox unit. Okay? Excellent. Any questions in queue? A lot. Okay. Well, we got some time for some more questions. Do we have one that is like different than the ones that we've been doing? Is it because if we can get one that's maybe of a different unit or a different topic area? Yeah, pick one, Maggie. So Maggie's taking this test tomorrow, so I'm really happy she's here helping because she could be at home studying, but she's helping because she's good to go, though. So Maggie, if there's any question there that looks like something that you would want to know, maybe that's a good. She's saying I already know it all. I know what she's thinking.
Got a question to go over the types of bonding.
Types of bonding, that's awesome. We didn't do anything about bonding. Thank you. Okay. All right, so the types of bonding. Okay, let's see. So when it comes to bonding, there's different ways that you can try to identify it all, and I'm going to try to go with the big idea. Okay, so if we're saying what type of chemical bond is there, then we want to be thinking of 3 different categories of chemical bonds. Okay, you can have what is called an ionic bond. You can have what is called a covalent bond. And you can also have a metallic bond, right? Covalent, ionic, covalent, metallic. So those are your 3 broad categories of bonds. Now, the reason I say you can go a lot of different places is because within those categories, especially covalent, there are many subcategories: single bond, double bond, polar, nonpolar, all that kind of stuff. So let's stick with these 3 categories, and then if there's any other question that goes deeper with this, we can do that, okay? All right, so what does it mean to be an ionic bond? Well, simply said, guys, ionic bonds must have a transfer of electrons, right? You have to have an electron go from A to B. And more specifically, from metal to non-metal is generally the way this works. So, as an example, the most classic example of an ionic bond is table salt, right? Ionic are crystals. The element sodium, in its elemental state, has 1 valence electron. So I'm going to draw 1 dot there, right? Now, it's going to bond to the element chlorine, and chlorine has 7 valence. So if I represent chlorine, I would say, and I like to do X's and O's. Some people like to do just all dots. Whatever you like is fine. But in an ionic bond, what's going to happen is you're going to have a metal element. You're going to have a non-metal element. And there has to be a transfer of electrons from the metal to the non-metal. So in other words, this electron is going to go all the way right there, and chlorine is now going to own that electron, which means I can redraw the sodium with no dots at all. It lost its valence electron, but in doing so, it lost a negative particle. It became a positive ion. Remember, we just said loss of electrons, charge goes up, right? So it became positive. Chlorine, well, chlorine had those 7 of its own, didn't it? But then it gained that one right there. Now, if I gain electrons are negative. That means that now I'm a negative ion now. I'm going to put brackets around that. You know why? Because chlorine owns those electrons. That's why we say the word transfer. That's an ionic bond. An ionic bond is transfer of the electron from the metal to the nonmetal, producing ions, opposites attract, and now they're stuck together into that crystalline solid, right? Okay. So that's the basic of ionic, right? What about covalent? Well, oh, by the way, remember, words mean something, right? We don't pick these terms arbitrarily. Why is it called ionic? Because it involves ions, right? You can't have ionic if you don't have ions. Now, covalent. Think about what that means, right? What does that prefix co mean, right? So cooperate, co-worker, right? There's another one I like to say, but I can't think of it. Okay, so cooperation, and then what's the other half of that word? Valent. That sure sounds like a word that we use all the time in chemistry, valence electrons, right? So here we are cooperating with our valence electrons, right? Now, I should have said something I didn't here. Is the whole point is that you're trying to get your stable octet, right? So in other words, when the sodium lost its valence electron, it was left with a 2-8. So let me write that there. And that means it's got its stable 8 valence, right? That's the stable octet. When the chlorine, which was a 2-8-7, when it gained an electron, it became a 2-8-8. So the chlorine also gets its stable valence, right? Its octet. So that's why the bond happens, right? They're seeking out stability. Okay, so what about covalent? Well, with covalent, we just said cooperation, right? And so what do we say? We say sharing. Sharing is caring, right? Sharing of electrons. A very wise woman used to always say, sharing is caring. I bet she still does. Sharing electrons, right? Now, how does this work? Let's say instead of the chlorine bonding with a metal, let's say it bonds with a nonmetal, right? Well, here's the problem, though. If it bonds to a nonmetal, nonmetals don't want to give away electrons, right? So I don't want to give you an electron. I need electrons. What are we going to do? We're going to share them. So let's say that you get chlorine to bond to the element hydrogen, right? Hydrogen has one electron. It's going to share that one electron with chlorine. Now, when that happens, look at these dots. Chlorine has 8 valence electrons. That's the octet that it needs, right? Hydrogen. Well, hydrogen's a bit of an oddball. It doesn't need an octet because it's so tiny. It only fills its first shell, so it only needs 2. But it got the 2 that it needs right there. That's your covalent bond, okay? So with the covalent bond, it's got to be the nonmetal plus another nonmetal, right? Okay. Let's see. Yeah, I think we're good there. Okay, and then the last one, guys, the metallic bond. And honestly, I think the metallic bond is the one that's probably least represented on the test. Simply because there's not, I'm sure if you're into metallurgy that there's a whole lot of complexity to metal bonds. But in terms of like your basic chemistry class, you don't get too involved in the little idiosyncrasies of metallic bonding. So how does a metallic bond work, right? Well, it's a little bit weird. In fact, I'll tell you in a second here, but let's say aluminum. Aluminum's electron configuration is a 2-8-3. So let's say I get a bunch of aluminums. Okay. All right, so I have a piece of aluminum foil, for example, right? Well, those are billions and billions of aluminum atoms, but the problem is they're all 2-8-3s, and none of them want to have those 3 valence electrons. They're all trying to get rid of those valence electrons. So how in the world does that happen? So what do we do in class to illustrate this? If you've ever played hot potato, right? So in class, take little racquetballs, and those racquetballs are your electrons. And we play a game of hot potato where one ball goes out. Now, as soon as you catch it, what do you have to do? You got to get rid of it. Got to get rid of it, right? So 1 ball, 2 ball, 3 balls. And then before you know it, all of these racquetballs are constantly moving around the classroom. Now, the occasional racquetball, bounces off someone's forehead, or maybe it breaks a beaker. It's all part of the fun, right? But what are we trying to illustrate here? These aluminum atoms are like playing that game of hot potato. They don't want it. As soon as the electron comes into their sphere, they get rid of it. And so these are gone. Say goodbye, 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 which means you get this, but then what happened to the 3, 6, 9 electrons? They are mobile. We use the word mobile electrons. 2, 4, 5, 6, 7, 8, 9. There you go. I think I counted 9. Those little electrons are basically moving around fluidly through the metal, which is really neat because it allows metal to do some things that ionic and covalent can't, right? One thing that metal does that's unique is that it's malleable. You can bend it, shape it, twist it. How can you do that? Because those electrons allow the atom's positions to be deformed, to be moved, right? The other awesome thing that metal does, I wouldn't have these lights blaring down on me right now if metal didn't conduct electricity. And it conducts electricity because of those electrons. Those moving electrons are what allow the electric current to move through that solid sample of copper or aluminum or whatnot, okay? So those are your 3 bond types, all right? Like I said, you could go into greater detail on all 3 of them, but those are your basics. Oh, you know what I did right here? Transfer sharing, and so we want to say highly mobile. Highly mobile electron is the way that we describe the metallic, all right? Okay. We're a little past 9 o'clock, but you guys got one more question? We'll try to do one more. One more good one? They're all good ones, I'll bet. No, Taylor said no, they're not all good. Just kidding, she didn't actually say that. got to be the last question. I just drank the last of my water. What you got?
Someone asked a question on significant figures and balancing chemical equations.
Oh boy, well that's two big questions. Okay, well let's see if we can do both of them. Balancing equations, that one we can do them. We can touch on both of them. Okay, thank you, Taylor. All right, so question was balancing equations and significant figures, which are totally different questions, but they're both going to be on this test. You're going to get a significant figure question. You're going to get a balancing reaction question, right? So let's look at the balancing reactions first. Let me see. I can write one down, but maybe if I look quick, I can get lucky and see if there's one. Because I do, hey, look at that. Now, this wasn't staged, guys. I picked up the first test, I flipped 2 pages, and I already found a question that says balance this reaction. So you're going to balance a reaction tomorrow. Now, how challenging that is, I have no idea, because I'm sure you remember when you learned how to balance reactions in class. You can have reactions that you can balance within 10 seconds. You can have ones where you can toil over them for 10 minutes. And I don't know if you'll ever get ones that are 10-minute ones on the Regents exam, but they will throw some out there that are not easy. And sometimes they throw ones out there that are relatively straightforward. So let's see what this one is. Balance equation number 1. Smallest whole number coefficients. All right, so what does it mean to balance an equation? Pink sheet. Balancing an equation means that you must follow the law of conservation. Charge, energy, and mass. Mass, atoms, right? Charge, energy, and mass have to be equivalent on both sides, right? Balancing reactions means that they're the same on both sides. So, if you look at equation number 1, let me put my little lines in front. You guys are going to have an answer sheet when you take the test, but even if the lines aren't there, you want to draw them because you want your eyes to know where to go, right? So here's what we got to do is we got to figure out what elements are not equal on both sides, and then we use the coefficients in front to multiply the formula to make them equal. Now, there's no one perfect way to go about this. The way that I like to do it is I tell my students, now there are some exceptions depending on the type of reaction that you're looking at, but generally speaking, your first approach is going to be to go one element at a time, sequentially through, and you fix as you go. But then, when you think you're done, you must go back to the beginning and do the whole thing again. And the reason is because as you're fixing the equation, you're also inadvertently breaking something. Maybe this reaction might give us an example. Let's look. Okay, so the first element that I have is the element nitrogen. Now here's my arrow right here. This arrow is the divider, right? I've got to make sure both sides are equal. I count 1 nitrogen atom on this side. I'm going to come over here. All right. How many do I have in it? Well, just that one right there. Okay, so nitrogen, you're already balanced. It's a 1 and a 1. Okay, move on to the next element. Don't try jumping around, okay? Next element is hydrogen, and it is H3. So I have 3 hydrogens on my reactant side. Now come on over. Uh-oh, I got a problem. That says H2. Now, I can't go any further until I fix the imbalance, right? Now, how do I fix it? The number in front, the coefficient, is a multiplier of the formula. So I have to put a number here to multiply the 3, and I have to put a number here to multiply the 2, and those numbers must result in the same number of hydrogens. So 2 and 3, what's a common multiple of 2 and 3? Well, if I put a 2 here, that means 2 times 3. That means 6 hydrogens. If I put a 3 here, that means 3 times 2, 6 hydrogens. I just balanced my hydrogens. And I also committed a horrible error because I'm using a pen. Don't use a pen when you're balancing. I hope this works out because if not, now I'm in trouble. Okay, yeah, don't use a pen while you're balancing because I might have to erase. Let's see. Okay, my next element is oxygen, and right there I have 2 oxygens, and then over here, oh no, let's see, there's 1 oxygen there, and then 3 times 1. Okay, this isn't that bad, right? Because if I say 1 oxygen plus, you see how that's 3 more oxygens there? 1 plus 3 is 4 oxygens total. So this whole side has 4 atoms of oxygen. Can I put a number there to do that? Yeah. I'm going to put a 2 there. Now I have 4 atoms of oxygen because it's 2 times 2 is 4. Okay. Now I'm going to go back and relook at this, and this is where I think I'm going to end up regretting what I did with my pen because, let's see here. Okay, I have 2 nitrogens. Oh no, I have only 1 nitrogen there. That's not going to work. All right, but then if I put a 2 there, it's going to screw up my oxygens. All right, so this is why I said use a pencil, by the way. But anyways, I'll scribble a little bit if I have to. Okay, so here's my problem. The oxygens are giving me an odd number. And if you think about, sometimes say that if you have an ugly odd number on one side of your equation, you have to get rid of it. Why? Because whatever number I put in front of that oxygen, it will always be even because it's times 2. So I've got to make sure that my oxygens on this side are also even. So what if I say, well, now I don't actually know the answer to this one off the top of my head, so you might have to toil with me through it. What if I double that 3 to a 6? That would make 12 hydrogens, which means I'd have to make that a 4, because 4 times 3 is 12 hydrogens. I'd have to put a 4 there, because 4 nitrogens. Now, why did I double the 3 to a 6? To get rid of the ugly odd number. Odd won't work. All right, now, okay. How many oxygens do I have? 4 times 1 is 4 oxygens, 6, okay, so I have 10 total oxygens on this side. Can I make 10 there? Yes, put a 5 there. Okay, sorry about the pen. 4, 5, 4, 6. Those are my coefficients. Now, can I reduce it? Because it said the smallest whole number ratio, right? Smallest. No, I can't reduce it. 4, 5, 4, 6 is unreducible, so that's good. Double check yourself. 4 hydrogens, 4 hydrogens. 4 times 3 is 12, 4 nitrogens and 4 nitrogens. 4 times 3 is 12 hydrogens. 6 times 2 is 12 hydrogens. I've got 10 oxygens and the 4. Okay, there we go. So in terms of the difficulty level, I'd say that one is creeping up there a little higher because you'd have to recognize that you can't have odd number of oxygens over here and that you'd have to up those numbers to get rid of the ugly odd number, okay? But that's the basics of balancing. The one thing I always tell my students too with balancing is it's maybe the one thing on this exam, maybe the one thing where trial and error, you can continually attack it from different vantage points. And when you feel stuck, leave it. Do something else and then go back to it with a fresh approach and maybe you'll see whatever it was that was causing you to get the hiccup there, okay? Okay, so that's balancing. We said that we would have one more question. We got 2 more, so we just did one of them. And the last question, which is a great question, guys, is significant figures. Now, oh, look at that. The very front of my little packet here has significant figures on it. Now, chemistry is the first class where I'm certain you had to learn significant figures. That doesn't mean that you didn't have prior teachers teach it to you. It's possible. But this is the first class where your Regents exam will test it, right? And so for a lot of us, it's a kind of a foreign idea. You know, what does a significant figure mean? Why does a 0 matter in some cases and not matter? Well, they all matter. The question is, does the 0 represent a measured value or is it just a placeholder, right? Now, if it's a placeholder, it's still important. It just means that it doesn't reflect a measured level of precision. So when it comes to significant figures, you can learn rules, memorize rules. And those rules will tell you when zeros are placeholders or not. Or you can use what we call the Atlantic Pacific rule. I prefer the Atlantic Pacific rule. The reason I prefer it is because it's simpler. It is always correct on this test. You'll always get the answer that you need. And it makes sense. It's straightforward. Okay, so let me show you what does it mean to be the Atlantic Pacific rule, okay? So in order for you to use the Atlantic Pacific rule, you have to have an imaginary United States of America in your head. So you got to know what the country's outline looks like, right? You got to know that the Pacific Ocean is over here on the left-hand side on the west coast, And the Atlantic Ocean is over here on the east coast, on the right-hand side, okay? Now, if you look at a number, and I'm going to put some other numbers in here rather than the ones here. Let's say that you have the number 20.010, right? You say, okay, and we'll put a unit on it, right? Let's call it grams, okay? How do you know how many of the numbers are significant? Well, anything that is not 0 is automatically significant because it means it was measured. You got it from a device, whether it was a balance or a ruler or whatever. But what about those zeros? There's 3 zeros in that number. How many of those represent significant figures? Well, here's where the Atlantic Pacific rule comes in. If the decimal is present in the number, then you will examine the number from the direction of the Pacific Ocean. Now, that means that I'm going to start over here on the left. I am going to begin examining my number from the left-hand side, and here's the rule, okay? As soon as you encounter a non-zero, you will begin to count significant figures, and you'll go through the whole number. They're all significant. So, in other words, the 2 is the first thing that I see. The 2 is a non-zero, which means right there, I start counting significant figures. How many do I have? 1, 2, 3, 4, 5. Every one of those numbers is significant. Now, what would be an example where you don't have it work out like that? Well, let's say that you're measuring something really small. Let's say that you are 0.0080, right? Okay, and we'll say meters, right? Maybe it should be in scientific notation, but we'll say meters, right? Well, how many significant figures are there? You got some zeros to contend with, right? Well, you know the 8 is significant. How do you figure out the rest? The Atlantic Pacific rule. Is the decimal present? Yes, it is. If the decimal's present, I'm going to examine the number from the Pacific Ocean. When I encounter a non-zero is when I begin counting significant figures. So, let's see. Keep going. Keep going. Keep going. Stop right there. The number 8. Now, as soon as I hit the number 8, that's where I begin counting the numbers that are significant. How many do I have here? I have 1, 2, 8, 0. So that number would have 2 sig figs in it, okay? Now, as far as the chemistry class goes, I will tell you, almost all the numbers we deal with in chemistry are going to be decimal present Pacific Ocean. Almost all of them, okay? Does that mean that you can't see something from the other side? No, you can, right? So we'll look at it, but most of the time the decimal is there, okay? So what would the other one look like? Well, let's say you had a number, 5700 kilojoules, right? So, you know, now that I think of it, often in the multiple choice questions, you might be seeing something like this, where there is no decimal, right? But rarely in data tables. Anyways, how do I know how many of those numbers are significant? Well, I know the 5 and the 7 are, but what about those zeros right there? Well, let's see now. Is the decimal present? No, the decimal is absent. That means I'm coming from the Atlantic Ocean. Now, where's the Atlantic Ocean? The Atlantic Ocean is over here on the right-hand side, right? But I'm going to do the same thing. I'm going to approach and examine the number from the Atlantic Ocean. As soon as I hit a non-zero, then I start counting. So, keep going. Keep going. Stop right there, the 7. 7, 5, 1, 2. There are 2 significant figures in that number. Let's look at one more. Let's say I have 90300, and we'll make that kilojoules as well, because that's the kind of kilojoule value you might actually see, although that's quite a lot. Is the decimal present or absent? The decimal is absent. So I'm going to approach this number from the Atlantic Ocean. Let's see. Keep going. Keep going. Stop right there, the 3. And now I count everything that goes after. 1, 2, 3. That number has 3 sig figs. Okay? All right. Folks, I think we're out of time for the night. That went really fast. some awesome questions. I hope you guys learned something. I hope that you're all feeling confident for tomorrow's test. Couple of parting words of advice, folks. Read your questions carefully, especially the short answers. The short answer questions on this test are often going to be written in a way that at least leads you in a direction of an answer. Read carefully. Make sure you're underlining and make sure that your answer addresses what is being asked, okay? Make sure you guys take your time. The test is at noon tomorrow. So I wouldn't sleep to 11:30, but you don't have to get up at 5:30 either, okay? Make sure you get a good night's sleep, all right? Other than that, guys, you've been working hard all semester. This is your parting event of chemistry, right? So you get to one last chance to show how much chemistry you've learned. Hopefully you guys have a good day tomorrow and you're happy with your results. Can I get you girls to come on up here and I'd like to thank Maggie and Taylor for coming here today, volunteering their time. They did a great job. Taylor took chemistry in this fall, so she's done with chem, but she remembers all of it. Yeah. Yes. And Maggie's going to be with us tomorrow taking the exam, and she's excited. She's done a lot of hard work. So 2 fantastic chemistry students. Thank you guys so much. Appreciate you coming here. All right. And good luck tomorrow. Take care.